So today's topic is u-substitution using exponentials and logarithms. Again, the good news is there are no big ideas here. If you know u-substitution, we're just going to add 2 more rules to it, and that's it. The same ideas of u-substitution still apply. And before we do anything about integrating using exponentials and logs, let's just remember these 2 basic properties. Does everybody remember that the derivative of e to the x is e to the x? Remember that was the easiest function there is, right, to differentiate? And just to remind everybody, what was the derivative of e to the 2x? Just a quick refresher of differentiation rules. If you had e to the 2x, what was the derivative there? Exactly, that would have been e to the 2x multiplied by the 2, right, from the chain rule, right? And like what if you had ln of a quantity, like ln of, before I get to it, let's refresh our memory. What is the derivative of ln x function? That was 1 over x, right? And what if I had like ln of a complicated thing, like ln of a quantity, ln of a function? Then you do 1 over that function times the derivative of the function, right? Like 1 over u times u prime. That's how we differentiate a complicated ln expression. Like just to remind everybody, before we go to integrals or antiderivatives, say if you had like ln of 7x plus 1, how would you differentiate this one? First you do 1 over the quantity, right? Times the derivative of the inside, which is, what is the derivative of 7x plus 1? It's 7, right? You can put 7 on the side or you can put it on the top if you like this. Either one would have been okay. So 7 over 7x plus 1, that would have been the derivative of the logarithmic function or ln function, which is the base e. Okay, so this was just a refresher of derivatives. But the main rules I want you to remember are the derivative of e to the x is e to the x, and the derivative of ln x is 1 over x. These were the principal rules, and everything else was a chain rule, basically, right? Okay. So today we're going to do integration. So let me ask you a question. What do you think will be the integral of e to the x? It'll be to the x, right? Because it's anti-differentiation. You think about a function whose derivative is e to the x. The answer is e to the x. So we find then that e to the x is not only the easiest function to differentiate, it is also the easiest function to integrate in a way because it's going to be itself. So derivative of e to the x is itself, and integral of e to the x is e to the x plus c. And sometimes you will see it in the u variable, like e to the u du. Same idea. If you're integrating e to the u with respect to u, the answer will be e to the u plus c. Okay, what about the exponential, rather the logarithmic function? So if we know the derivative of ln x is 1 over x, what do you think will be the integral of 1 over x? The antiderivative of 1 over x will be, think of a function whose derivative is 1 over x, and the answer is ln x. So therefore, the integral of 1 over x is going to be ln x. And here you'll see absolute values. The reason is 1 over x is actually defined over the entire real numbers except for 0, but it's well defined for negatives, whereas the ln function is not. And to make them compatible, if you just take the absolute value of the answer, ln argument, like ln of the absolute value of x, then it works out fine even for negative x values. And again, I wrote the rule for you in terms of u as well. 1 over u du, the integral of that is the same as ln of absolute value of u plus c. Now, sometimes you're going to forget about this rule, but you may have a situation like this. Let's say that you're trying to integrate, say, the integral of, let's say you have 1 over x dx, and you totally forgot about the natural log function. You might be tempted to do the following. Okay, let me write it first in terms of a power. Okay, so you write it as x to the minus 1, and let me try to apply the power rule. If you apply the power rule to this, what happens? Add 1 to the power, you have x to the first power, right? I'm sorry, x to the 0th power. Negative 1 plus 1 is 0, right? Now try to divide by 0, undefined. So you can see here that our good old exponent rule for anti-differentiation, it just doesn't work when the power is -1, you see? So then you might say to yourself, okay, there was something else. What was it? Maybe that will force you to remember, okay, the integral of 1 over x is going to be ln x. If nothing else, this rule of adding 1 to the power and dividing by that new power, it just doesn't work for this case. So we need a new rule, and in this case, the answer comes from the natural log function. All right, so now that we know these two rules, we're going to be solving some examples. Let's start with something simple. Say integral of e to the 2x dx. There aren't that many choices here. What would you suggest that we select as our u variable? Pardon me? How about 2x? Let u be 2x. So the derivative du will be the derivative to the right-hand side, which is 2 dx. We come back to our integral and try to rewrite it as we have always been doing for these questions in terms of the u variable. Instead of e to the 2x, what can I write? E to the u. Instead of dx, what can I write? If you solve for dx here, you will get du over 2. And 1/2 can be factored outside. Now, what do we know about the integral of e to the u du? Again, it's the easiest function to integrate. It's going to be itself. So that gives us 1 over 2 times e to the u plus c. And as always, replace the u back with its equivalent. You get 1/2 times e to the 2x plus c. Now, I want us to look at this example and tell me, could you have done this question without using u-substitution? Can you tell me a general rule that I can use from now on that doesn't even require u-substitution? If I have the integral of e to the constant times x, what do you think the answer will be from now on? Divided by the constant, exactly. So if I write it again, so if, in general, I can use the following as a rule. If I have the integral of e to the kx, where k is a constant, without even using u-sub, I should be able to write down the answer will be e to the same constant times x divided by the constant plus c. And again, this is very similar to something we reviewed earlier, which is like if you have like integral of, let's say, sine of 3x or sine of kx. What was the antiderivative there? First, the antiderivative of sine was negative cosine, right? And then you divide it by the constant of 3. Whatever the constant k may be, you divide by it. Again, in that regard, it's completely opposite of differentiation, right? In differentiation, you multiply with that constant. In integration, you're dividing by that constant. And that makes sense because if you were, going to anti-differentiate something and then check your answer, you should be able to get the original quantity back. So if you were to differentiate this, there's going to be times 3 coming in, and that this 1/3, they're going to cancel each other, so you can come out with the original function. So this is a very important rule to know without having to use u-sub. Once again, in differential equations, you're going to see this pretty much, I would say, every single day. It's like one of the most basic integrals you're going to be required to know. So it's very, very important. This is really the time to learn it, to memorize that rule. Okay, let's take a look at the next one. Integral from 0 to 1. 3x times e to the x squared plus 1. I'd like to give you a few moments before we solve this one. Let's take a look at the solution. So I'm going to let u be x squared plus 1. Again, in general, we want u so that its derivative is already in the integrand. In this case, derivative of x squared plus 1 is 2x dx, and I already have an x dx in there. We don't worry about the constants because we can always manipulate them around this integral. So I'm going to differentiate both sides, get 2x dx. The 3 can be factored outside. This quantity will be e to the u. And what about the x dx? X dx is du over 2. So I will just plug that in here, du over 2. And again, at the moment, I'm not putting the limits of integration because those limits are set for the u variable, right? I'm sorry, for the x variable, so I don't want to carry them for the u variable. I will bring them in only after I've brought the x variable back. Okay? At the moment, just don't forget about the limits of integration. Just do the anti-differentiation. Again, this is the easiest one to integrate, right? E to the u itself. Now let's bring in the variable x, in this case, x squared plus 1. Before I go any further and plug in my limits, I want to check my answer. So let's differentiate to see if we get what we started with, right? To differentiate this, the derivative of e to the u is e to the u times u prime, right? What is u prime here? 2x. The 2's cancel. Did I get back what I started with? 3x e to the x squared plus 1? Definitely, right? So it is indeed the correct antiderivative. Now let's plug in the limits. When I have a constant up front, I like to factor it outside. First, plug in 1. 1 squared is 1, so we have 1 plus 1 or 2. E to the second power minus, plug in 0. E to the 0 plus 1 is just e to the 1. We could leave the answer like this. We can take out an e and leave it like this. Or we can get a decimal answer. Just let's use our calculator. To get e, usually you have to do like second ln and then e to the first. And my calculator also has a separate e key on the top of the division sign right here. If I do second division sign, it will also give me an e exact value on the calculator. So let me give you guys a moment to calculate this. Please let me know what you're getting. Please let me know if you have a value. .00. So let's just say roughly to the nearest whole number, or even to the tenths, it's roughly 7.07. Okay. So the important thing to remember with the limits is to wait until you brought back in the original variable. Now there is also another way to evaluate limits. I want to show you this because sometimes I talk with my good friend Professor Jordan, who teaches physics, and she says this is the way she does them, and then sometimes students are confused because they've never seen it before. So I want you guys to also know that it is possible to do limits like this. So basically we're going from the x's to the u's. Okay, the limits for the x's were 0 to 1 as given, right? Now u is x squared plus 1 as by our choice from earlier in the problem. What is then u? If x is 0, what is u? Just plug in a 0 for x, right? You get u equals 1. Would everybody agree? 0 squared plus 1. Okay, now plug in a 1 for x. What do you get? 1 squared plus 1 is 2. Okay, so basically you can go, limits for x are 0 to 1, and limits for u are from 1 to 2. So if you wanted to, you could come right here. After you took your antiderivative, and while you're still in terms of u, you can also plug in your u limits, which are from 1 to 2. So then the answer would have been 3 over 2 times, again, put the upper limit minus put the lower limit, e squared minus e to the 1. It's the same thing, right? As we got earlier, e squared minus e to the first power. So either way you do it, it will be the same thing. The important thing to remember is, if you are going to put your limits for u, make sure you've converted them in for limits for u. If you're going to use the limits for x, then bring back the original variable x, and then use those original limits with that variable. Either way you go, you should get the same answer. Okay. Another question? Any problems? Any questions about the solution before we try another one? Okay. Not that one. Let's try some of these on this page. Starting with the first one, I want to give you a moment to think about it. So a good choice for you is cosine x, because this derivative is already in the given integrand. So I'm going to take out the 5 as usual, pulling out the constant. E to the cosine x now becomes e to the u. And the sine x dx, what should I be replacing that with? Du or negative 1 times du? Negative 1 times du, because if you solve for sine x dx down here, you will get negative 1 times du, right? So I can take the negative outside and then keep the du on the inside. Again, a few important things to pay attention to when you're writing your answers. Once you take the antiderivative, you should no longer keep your integration sign, and you should no longer have the du hanging around anymore. That's just a notation we use with the integral notation. So here, the antiderivative of e to the u is e to the u. So I've already taken the antiderivative, so I no longer need the integral sign, but I do always have a plus c at the end. And this plus c turns out to be really important in differential equations. Like if you forget it, you lose like an entire half of a long question. So it's a good habit to get into early on. Okay, and then put the u back in. And there we have it. Any questions on that one? Okay, so let's try the next one. Now we're entering the zone for logarithmic functions a little bit. So we've been doing examples of the exponential function integrals. This one will require the other formula, the one with ln absolute value of x. So this one seems like a typical question in u-substitution, right? Let u be x squared plus 1. Again, that we know is a good choice for u because its derivative is going to bring in an x dx, and there's already an x dx on the top, right? So let's differentiate both sides. Take out the 7. Now on the bottom, I'm just going to have a u. On the top, for x dx, what should I be writing in? Du over 2, right? Because 2x dx is du. So what about x dx? X dx is du over 2. Now, how do we integrate 1 over u du? That's going to be the natural log function. Again, if we try to apply the power rule, you have a u to the minus 1, you're going to run into the same problem we discussed earlier, right? Add 1 to the power, that will force you to divide by 0, which is undefined. As we can see, that rule does not work when you have u to the minus 1. But luckily, we know that there's another rule, which is ln of the absolute value of u. And last step, as always, is to replace the u with its equivalent. How could I check this answer? Differentiate the answer, and that should give us what we started with, right? At the moment, just don't worry about the absolute value. Say those are parentheses. As a matter of fact, x squared is always positive, plus 1 is always positive. For this question, you really don't even need the absolute value. This quantity is always positive anyway. So how do we differentiate this? 7 over 2 times. The rule was 1 over u times u prime, right? Okay, what 1 over u will be? 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. The 2's cancel. Did we end up with what we started? Yes, 7x over x squared plus 1. So indeed, we know this is the correct antiderivative. Again, that was just our checking process. Now the next one seems unusual. You might say, wait a minute, haven't we already talked about derivatives of trig functions and also the antiderivatives of some trig functions? Yes, we have. We can find the antiderivative of sine, the antiderivative of cosine. We can find the antiderivative of secant times tangent, which is what? Secant x, right? And what about the antiderivative of secant square? tangent, because there is tangent in secant squared. But we've never talked about the integral or the antiderivative of the tangent function. The reason is you need something that you're learning today in order to be able to do that. What would be a good start if we have no idea what the answer is? We're dealing with a tangent function. What might be a good approach here? Excellent. So many of you said that. Sine over cosine. Write tangent in terms of its equivalent, because we know a few things about sine and cosine function, and let's see if we can make use of them in this question. So tangent is sine over cosine. Okay, now what could I do? I heard u-substitution with u equals what? Let u be sine or cosine, which one? Only cosine will work. The reason is if you let u be cosine, its derivative is going to bring in a negative sine x dx, and you have that in the numerator. If you try the other, u be sine x, its derivative is cosine x dx, but cosine is not in the numerator. That's not going to work. So let u be cosine x, so its derivative is negative sine x dx. So now this integral becomes, the bottom is u, and what should I write for sine x dx? Pardon me? du or negative 1 times du? Negative 1 times du, right? Because sine x dx is, so if you solve here for sine x dx, that's negative 1 times du. So I should put the negative outside and the du on the inside. Now what can we say about the integral of 1 over u du? Exactly, negative ln of the absolute value of u plus c, and then putting the u back in, get ln of cosine x in absolute values plus c. Now I want to caution you against a very common mistake I see, and this will cost you. If you make this mistake, and if there's like 3 questions like that on the test, that would be very, very costly mistake, so please don't do this. What I see is, like, after we've learned this section with the natural log, say students see something like this on the test, say 1 over u squared du, and many times students will write, please do not do this, ln of u squared, something like this. Okay, can I do this? Definitely not. What should I be doing instead? Any other power other than 1 over u or u to the negative 1, any other power, you should use the power rule, right? The power rule. So how should you be doing this one? First, write it down as u to the negative 2nd power, right? Then add 1 to the power, divide by the new power. This will turn out to be, I believe, negative 1 over u. That's the way to do this one. The only time you use the natural log is if you have a situation like this. Exactly in that situation, 1 over u du. That cannot be done with the power rule there. We're going to need the natural log function. Okay, another example.